Hello friends, good morning. I am going to discuss about the theoretical background principle, instrumentation and finest applications of gel filtration or gel permeation chromatography. So in my lecture, I will be introducing the uh, technique, and then I will be discussing about the principle, then what is the influence of stationary phase gels, and how we have to set up this experiment, and finally the applications of gel filtration. This technique is actually termed as size exclusion or molecular sieve or gel chromatography or gel filtration. Very famously, it is termed as gel filtration. This is the most powerful technique which is used to purify or separate high molecular weight entities like proteins or polymers of carbohydrates. We can easily purify or separate by effectively implementing this particular technique. What is the simple overview or outline of this technique is you can elute different molecules based upon different degrees of steric exclusion, which is done with the help of your gels. That is, molecules will be separated based upon their size, which is related with your weight. So here the primary parameter is your molecular size and the secondary parameter is your molecular weight. So the molecules which enter into the column will be separated purely based upon molecular size rather than molecular weight. So this technique was proposed by two eminent scientists, Porath and Floden, in the year 1959. They used Sephardex gels as a stationary phase material. So what is Sephardex? In subsequent lectures I will be discussing. The principle of this technique is very simple. We are going to separate different analytes based upon the molecular size, which is the primary parameter. Size and shape will be the primary parameter. That is the direct principle. And the relative molecular weight will be the indirect principle. Now here you can see in this picture, in this image, there are three different molecules varying in their size. So one yellow color, this particular molecule, the size is very small, and this dark yellow color, the size is moderate, and the red color molecule, you see, the size is larger. So the larger the size, the molecules will very fastly travel through the column and will get eluted, followed by this thick yellow color moderate size molecule, and then followed by dull yellow color small molecule. So the separation is purely happening because of the molecular size rather than molecular weight. So what type of stationary phase, how we are going to separate? Again, there will be a stationary phase which is filled with gels, and we have to equilibrate the column with the help of the mobile phase or the eluent, which we are going to use in the experiment. So here the larger size molecule will be excluded by the gel. That is why the technique name takes us gel exclusion, means the larger size molecules cannot enter into the gel because the pore size is too small. So you can see the red color, they are totally excluded by the gel. So the concept or the principle is very simple. Larger molecular size molecules will be excluded by the gels, they cannot enter into the gel, whereas small molecular size molecules, or if the size of the molecules is lesser than the pore size, they will be included inside the gel. So this distribution is happening with the help of the mobile phase or the eluent. So like planar chromatography, gel filtration is a type of column chromatography. Here again there will be a stationary phase and there will be a mobile phase, and the separation primarily will happen because of molecular size. Now here you can see this is the architecture of a single gel. You can see in this gel the size is little bit larger. This is the pore size, and here there is another gel with the smaller pore size. Again there is another gel. You can see you can prepare gels with the different pore size. Again that I will be discussing in the subsequent lecture. Large pore size gel and small pore size gel. You can see you take this large pore size gel. There are say 7 different molecules. Out of 7 molecules, Four molecules size is very smaller, so they are included inside the gel. That means they can diffuse into the gel. Whereas larger molecular size molecules, they cannot enter because the pore size of the gel is very smaller, so they are excluded. Now this is the principle how macromolecules got separated. Second thing, you can see the hydrodynamic volume. Now you can see 5 different molecules. So here the molecular weight is 5 kilodalton and the molecular size is 2.45 nanometer. So here 15 kilodalton, the size is 3.53 nanometer. 35 kilodalton, size is 4.69 nanometer, and it is 65 kilodalton, size is 5.77, and the larger molecular size molecule whose size is 6.54 and the weight is heavy. Now here you can see the molecular size is directly proportional to the weight. That is, the myth is when you increase the molecular size, automatically the molecular weight will be also increasing, right? But still we are using molecular size as a primary parameter due to some reasons which I will try to cover in my lecture because that is beyond the scope. So pore size and the hydrodynamic volume or the molecular size of the molecule, these two things are connected with each other for effective separation. Now first we will discuss about different types of stationary phase material which can be used in gel filtration. The very first one is very prominent and famous Sephadex gels. There are different types of Sephadex gels. Say Sephadex G25 or G50 or G100 or G200. These are the different types of Sephadex gels. And here you can see the cutoff size, the molecular weight cutoff size is denoted in the right side of the table. For G25, this is the gel whose pore size will allow the molecules up to a molecular weight of 4500 daltons. So this is smaller pore size gel. Whereas G200, you can see this is the larger pore size gel where it allows the molecule up to 200 kilodalton. So you should have finest idea about your molecule of interest. You should know the molecular weight of your molecule of interest. Then only you can select the type of the gel which you want. So what is actually Sephadex? Sephadex is nothing but dextran based gels. Dextran, it is a polysaccharide primarily made up of glucose residues. Usually Sephadex available as a powder, you can see is the powder. Sephadex as powder, it is available. And when you soak this Sephadex powder in buffer or in water, exclusively in buffer is preferred, it will swell, so that you will be getting bead or gel like architecture. So if you want to perform this experiment immediately, you cannot perform. You have to take the Sephadex powder and you have to soak the Sephadex powder in the appropriate buffer with appropriate pH for overnight. At least 12 to 16 hours soaking time is needed so that the beads will swell and you will get gel-like architecture. Now here it is gel-like architecture. So there are various types of gels, Sephadex gels, as I discussed. Now what these numbers denote, G25, G50, G200, 100, what these numbers denote? These numbers denote the water regain capacity. That is, for example, water regain capacity which we have to multiply it by factor 10. That means if it is G25, if you multiply by 10, you will get 25 or 50 or 75 or 100 or 200. If you multiply the water regain with the gel. So that means here if you want to calculate the water regain capacity, you have to divide by 10. So 25 divided by 10 it is 2.5. 200 divided by 10 it is 20. Suppose you take G200, you divide by 10, you will get 20. That means per gram, that is 1 gram of Sephadex can hold 20 grams of water. Now in the case of G100, you divide by 10, 100 divided by 10, you will get 10. That means 1 gram of Sephadex powder can hold 10 grams of water. So you calculate the density of water is 1 gram per ml. So when you say 20 gram of water, that means 20 ml of water will be occupied. When you say 4.5 gram of water, it holds 4.5 ml of water. So here for G200, you divide by 10, you will get 20. That means 1 gram of gel approximately can hold 18 to 20 ml of water. So you can calculate the water content, and you can increase or slightly you can decrease, so that you can create a fantastic gel-like architecture. So here in Cephaladex, the numbers denote water regain property. And you can cross-link the gels. Now here you can see how to cross-link the gels. You have to cross-link this is a single gel. So you want to create a gel bead, how to cross-link. So you can use epichlorohydrin. This is the most preferred cross-linking agent exclusively for Cephaladex, for creation of Cephaladex gels. So the dextran matrix can be cross-linked with the epichlorohydrin. So you can produce different pore size. When you increase the concentration of cross-linking agent, automatically the pore size will be decreased. Now you can see the pore size of G25 is very smaller because it allows only protein up to 4.5 kilodalton, whereas for G200 it can allow the protein molecules up to 200 kilodalton. So the pore size is larger for G200, pore size is smaller for G25. So here you have to use less concentration of epichlorohydrin, so the pore size will be larger. Whereas in G25 you have to increase the concentration of epichlorohydrin, so the pore size will be smaller. You can see the weight is molecular weight is directly proportional to the size. So lesser the molecular weight, lesser the pore size, larger the molecular size, larger the pore size. So you can create the pore size based upon the concentration of epichlorohydrin. So this is very very important. And how the molecules that enter into the gel is folded, that is the interaction force formed between the analytes or the gel, like dipole or van der Waals or hydrogen bonding. Usually, primarily hydrogen bonding is preferred because this is a polysaccharide. The nature of the gel is a polysaccharide. You know, polysaccharides contain polyhydroxyl group. So the primary non-covalent interaction which is happening between an analyte and the gel is hydrogen bond. So please remember, non-covalent interactions play a major role in holding your molecules inside the gel. It's not outside the gel. Here you can see this is one dextran and this is another dextran. So dextran is a polymer made up of glucose. This is one dextran sheet. This is another dextran sheet. Two dextran sheets were connected by epichlorohydrin. So now you can see the structure of epichlorohydrin. So now you can see this is one epichlorohydrin, this is another epichlorohydrin. Now this is the pore size. When you put one more epichlorohydrin over here, then the pore size will become smaller. When you remove this epichlorohydrin, the pore size will become larger. So Cephaladex gels with a different pore size can be formulated by varying the concentration of the cross-linking agent, that is your epichlorohydrin. The next station of this material is polyacrylamide gels, which is termed as biogel. This is the commercial name. So this is like your polyacrylamide gel electrophoresis. The mechanism, the phenomenon is same. So what we are using in polyacrylamide gel electrophoresis page, same phenomenon is applied over here. There will be monoacrylamide. The monoacrylamide will be converted into polyacrylamide in the presence of APS, that is ammonium persulfate, and where you will be using intermediate as a free radical generating catalyst. So ammonium persulfate will generate the free radical, and the generated free radical will attack the monoacrylamide. So as a result, you will get polyacrylamide. So in the case of Cephaladex, glucose polymer is the polymeric sheet. Now here polyacrylamide is the polymeric sheet. There you are using epichlorohydrin. Here you are using N prime methylene bis acrylamide. So the phenomenon is same. As Cephaladex gels or polyacrylamide gels, the phenomenon is almost same. Only the chemical composition will vary. Here one polyacrylamide sheet will be connected with another polyacrylamide sheet using a cross-linking agent. The cross-linking agent is N prime methylene bis acrylamide. Similarly, You can when you increase the concentration of cross-linking agent, the pore size will become smaller. When you decrease the concentration of cross-linking agent, the pore size will become larger. So if you want to have a larger pore size, use low concentration of cross-linking agent, that is N prime methylene bis acrylamide. If you want to decrease the pore size, then use high concentration of cross-linking agent. The phenomenon is same, the method is also same. If you want to do the experiment, if you want to perform the experiment, take the dry powder of polyacrylamide, take the dry powder of polyacrylamide, you soak overnight say 12 to 16 hours so that it will swell, you will get a gel architecture. Now the gel architecture can be used. Now here the number, you can see biogel P2, biogel P10, biogel P300, biogel P300. You will be having different varieties of biogels, but here the number denotes totally different. Here it denotes the exclusion limit directly. 2 means proteins or any high molecular weight molecules up to a weight of 2 kilodalton will be allowed inside the gel. It will be included inside the gel. Beyond 2, so there is a molecule with the weight of 3 kilodalton or 5 kilodalton. Those molecules will not be included by the gel, they will be excluded. Similarly, 300 means 300 kilodalton. If there is a molecule with the 301 kilodalton, that molecule will not be included by the gel because the size will be slightly larger than the pore size. So those molecules will be excluded. So here the number, the gel number P2 or P10 or P50 or P100, directly it includes the exclusion limit. Now here how the molecules are interacting with the gel, again the same non-covalent interactions, but here preference will be given to hydrophobic rather than hydrogen. In the case of Sephadex, the primary interaction is hydrogen, whereas in polyacrylamide, the primary interaction is hydrophobic, because you can see hydrophobic backbone. So CH2, CH, CH2, CH, CH2, CH. The backbone, acrylamide backbone is highly hydrophobic. So hydrophobic interactions will predominate. So any molecule with having more hydrophobicity will enter into the gel, and it will be held by the gel for a longer time than other molecules. So the primary interaction is hydrophobic, then even dipole, and to a small extent dipole, hydrogen bonding and van der Waals interaction will contribute. Third one is again same, it is agarose gel, where agar is nothing but a linear polysaccharide which is made up of galactose and 3,6 anhydrous L-galactose. This is equal to the agarose gel which we are using in agarose gel electrophoresis. So, sorry, the phenomenon is same. If you want to have increase the pore size, and then you increase the concentration of the cross-linking agent. If you want to decrease the pore size, you decrease the concentration of the cross-linking agent. Only thing is the cross-linking agent, the type of cross-linking agent what we are using will be different from Sephadex to polyacrylamide and polyacrylamide to agar. The phenomenon is same. Again here you have to, if you want to swell the gel, you have to slightly soak it and you can prepare it, right? The possible interactions are hydrogen, dipole and van der Waals. Now here you can see the architecture of the agarose gel. And again there is another type of special gel. It is a mixture of dextran and N-methylene bis acrylamide. It is actually termed as cefacryl gel. Only thing is it can bear high pressure rather than other gels. So the breaking of the column bed is little bit difficult. So it can withstand the mechanical pressure when compared to Sephadex or biogels or whatever it may be. So the phenomenon again it is same. So here you can see if you use dextran gels, that is Sephadex, you can separate the molecules with lower molecular weight. It is good to separate or to purify low molecular weight molecules. But if you have decided to go for a larger molecular weight molecules, better you can go for agarose. You can see you can separate molecules up to 40,000 kilodalton, whereas here it is up to only 600 kilodalton. So if your interested molecular weight is less, then you prefer dextran gel, that is FRDEX. Whereas your interested molecule weight is larger, it is very, very huge. Weight is 1000 kilodalton or 1500 kilodalton or 5000 kilodalton. Better you can go for agarose, or even you can go for dextran with acrylamide. So selection of the type of the stationary phase is purely dependent upon the molecule of your interest. Which molecule, what type of molecule you want, and what is the nature of the molecular weight. It is a larger molecular weight or it is a smaller molecular weight. You carefully observe and then you select the appropriate stationary phase. Now I will slightly discuss about the theory. Now here you can see the total volume of the column. Now this is the entire column. This is the total volume of the column. This total volume of the column is actually termed as VT. That is the total volume. This total volume is contributed by three things. One is VG, another VI, another one is VO. So what is VG? Is the volume occupied by the stationary phase. That is G denotes gel. So volume occupied by the gel beads, maybe Cephadics or Biogel or whatever it is, volume occupied by the gel beads, and Vi is the volume occupied by the mobile phase which is present inside the gel. Here you can see this is the Vi. So here the volume of the mobile phase which is present inside the gel. So this is Vi, right? Now, what is VO? VO is void volume. That means volume of the mobile phase which is present between the gel beads. Now here you can see, so this is one gel, it's another gel, the third gel, fourth gel. So between the gel interstitial spaces, you see this volume is occupied by the mobile phase. So you please you observe this green color. The mobile phase which is occupied between the gel space or between the interstitial spaces of the gels. So this volume is actually termed as void volume or VO. So you have to remember the three volumes. The entire column is occupied by stationary phase based gels VG. Mobile phase we are discriminating into two types. Mobile phase distributed outside the gel, mobile phase which is distributed inside the gel. So now we can use here the elution volume is very important. Once the sample addition is over, we have added the sample to the top of the column. Now separation got over. Once separation is over, we have to collect the separated entities. We have eluted. We have to elute it. So for that we have to select the appropriate eluent. Sometimes the mobile phase itself can act as an eluent. Sometimes you have to put some strong eluents. So what volume of eluent? How to calculate the volume of the eluent? For that we can use this formula. V is equal to VO plus KD into VI. V is volume of eluent or volume of the mobile phase what you are using. VO is void volume, that is volume of the mobile phase which is present between the gels. You can calculate the void volume by using the blue dextran. Blue dextran is commercially available. You can add blue dextran, and blue dextran will not enter into the gel and it will pass between the gel. You can and easily you can elute the blue dextran. Since blue dextran is blue in color, the total disappearance of blue color from the column shows that the entire blue dextran was eluted. You measure the volume using a measuring cylinder. So it could be 20 ml or 40 ml or 50 ml. So that will be the void volume. So calculation of void volume is very easy. You can use the one marker molecule, that is blue dextran. KD is actually distribution constant. VA is actually the volume of the mobile phase inside the gel, or the gel which is holding the mobile phase inside, that is VI. So you can expect three different distribution values. KD can be equal to 0, KD can be equal to 1, or KD can be greater than 1. So it could be 1.5 or 2, 2.5, whatever it may be, greater than 1. So what happens when KD is equal to 0, right? Now how to calculate the KD? You keep KD here. So VE When you bring this VO to the left side, it will become VE minus VO, and when you bring this VI to this left side, it will become VE minus VO divided by VI. So elution volume, the total elution volume, you subtract with void volume, you divide by very simple your volume of the mobile phase which is present inside, you will get the distribution constant. So you can calculate the elution volume, you can calculate the void volume, you can using blue extent, you can calculate the volume which is present inside. So this will give the KD value. Now, what is the interpretation? Right? Suppose if KD is equal to 0, use this equation, you apply KD is equal to 0. So 0 into VI it will become 0. So when KD is equal to 0, VE is equal to VO. So that means if the elution volume what you have used is equal to the void volume, you can't separate the molecules which is present inside the gel, because this volume is insufficient. This is exactly equal to the void volume. So this could be used to push the molecules which is present outside the gel. So when KD value is equal to 0, the elution volume is equal to the void volume. So the calculated elution volume is insufficient. You have to increase it. So that is the piece of information. Whereas when KD is equal to 1, right, that means you substitute the KD is equal to 1. So 1 into VI will become VI. So elution volume is equal to VO plus VI. That means if you want to eluate the molecules which are stuck up inside the gel, you should you have to prepare an elution volume which is summation of void volume with the volume of the mobile phase which is present inside. So VO plus VI. If VO is 10 ml, VI is equal to 10 ml. So you have to prepare 20 ml of VE. So when you prepare 20 ml, you can 20 ml or it can pull the molecules. It can disconnect the interactions between the gel and the molecules which are stuck inside, and thereby the low molecular weight molecules which are present inside the gel will pass away. So double the volume. So you have to summate the void volume as well as the volume of mobile phase which is present inside. These both volume 5 ml of VO and 5 ml of VI, total 10 ml. So use 10 ml of LU1 volume for effective elevation. If it is 10 ml of VO and then 15 ml of VI, for example, you have to put 25 ml. So elution volume is summation of void volume and volume of mobile phase which is present inside. Whereas if the KD value is greater than 1, say here the void volume is 10 ml and the VI is 10 ml, exactly you have to go for 20 ml. Suppose you have prepared 30 ml higher, so automatically the KD value will become higher, right? So when KD value is greater than 1, here you can use it up. Say V is equal to 30 and this is actually 10. So 30 minus 10 is 20 and VI is 10. So 20 divided by 10 you will get 2. So the KD value is greater than 1. That means the analytes will be adsorbed to the gel surfaces. Either the analytes should pass between the gel or the analytes should enter into the gel. Whereas here the analytes were totally adsorbed. So again the effective elution will not happen. So the eluent volume should be it should be equal, exactly equal to the summation of void volume as well as VI. See, when you calculate KD is equal to 0, and interpretation is different. When KD is equal to 1, again it is complete inclusion. When KD is greater than 1, then the analytes got adsorbed. So what is the step 1 instrumentation? You can see the gel bead, the single gel bead, and this is the inner portion of the gel. This is a scanning electron micrograph. So this is the inner portion of the gel, right? Gel architecture, sorry, gel architecture, a big gel architecture, which is having a different pore size. One gel, which is having the pores. So the pores will be present here. So the molecule can enter into the gel. So this is a single gel architecture having pores. So from outside, molecules can enter inside. So select the appropriate stationary phase, use appropriate buffer, and then you keep this for overnight, that is 12 to 16 hours, so the gel will swell. The purpose, you can see the properties of a stationary phase material is chemically it should be inert, mechanically it should be stable, it should create some pores with uniform pore size. The gel should be stable with the to some extent of temperature, pH and other organic solvents. The gel should not get distorted. So this is very important. And you can equilibrate the gel. When you add gel slurry into the column, you equilibrate with the mobile phase what you are going to use it. See that the gels should not dry. This is very important. Now pour the gel slurry very gently into the column. Air bubble should be avoided. Then step 3, you wash the column or equilibrate the column with the elution buffer or the mobile phase. So it's not mandatory that you have to use a mobile phase separately and elution solvent separately. Sometimes mobile phase itself can act as a good eluent. So it all depends upon the molecule which you are going to separate, right? So step 3, you wash the column with appropriate mobile phase or elution buffer. See that the air bubble should not be formed. If it is, it should be removed. And there should not be any crack in the bed. So repeatedly wash the column until getting a uniform bed setting. And then you can put a small filter paper to the watermelon filter paper to the top of the bed, and then you can gently apply the sample. So the volume of sample should be very less. Should not add say 5 ml or 7 ml or 8 ml, right? It should be 0.5 ml to 1 ml. So that is the standardized volume. Use appropriate volume, not large volume. So small liquid of sample is applied gently. And you see the main important point, the sample should not be viscous, it should be very clear. You select appropriate mobile phase or eluent, and then you add the eluent or the mobile phase to the top of the sample. So what happens, you see the mobile phase will carry the heterogeneous mixture which contain different types of large molecular weight molecules. So the molecules will be distributed into the column, and based upon the size, the molecule either it will enter into the gels or it will pass between the interstitial phases. So higher molecular weight molecules beyond the cutoff pore size, they will pass between the interstitial spaces of the gel very quickly. It will get sedimented, and when you open the stopper of the column, when you open the stopper, the large high molecular weight molecules will get eluted first, and small molecular weight molecules, since they have entered into the gel, you have to use appropriate eluent or you have to use appropriate the same mobile phase. So the mobile phase will disconnect the interaction between the molecules and the gel, and the mobile phase will interact with the molecules. It will pull the molecules outside the gel, and then the analytes or the molecules will pass between the interstitial spaces, and then it got eluted. So the concept is higher molecular weight molecules will pass through the column first, and lowest molecular weight based molecules will pass the column last. So that is the phenomenon. So you can maintain appropriate flow rate. The universal flow rate is 0.25 ml to 5 ml. You can fix it up 1 ml per minute or 1.5 ml per minute or 0.5 ml per minute. You can fix according to the type of the molecule which you want to separate or purify. And you can detect, even you can couple with some detectors, and you can even detect the separation of the molecules like UV detector, refractive index detector, fluorescence detector. You can use it. So what is the application of gel filtration? You can purify peptides, proteins, enzymes, large molecular weight based proteins of different varieties. You can purify or separate. You can determine the molecular weight of the molecules. Either it may be a protein or it may be a polymer. you can determine the molecular weight. There is another important application. You can separate nucleic acids, you can remove endotoxins, large molecular weight endotoxins, which is toxic to the human population. You can remove it. You can even remove salt contaminants. Even though for removing salt contaminants, the most preferred technique is ion exchange chromatography. To some extent, you can use gel filtration. You can use low pore size Cephadic gels like G25 to separate salt contaminants. So, as I said, one important application is determination of molecular weight. You can see when the elution value is very less, that means you are not struggling a lot. The volume is very less. That means already the molecule is present outside the gel. It has not entered inside. It is not included inside the gel. It is excluded by the gel. So only less amount of mobile phase is required to elute that particular molecule. So high molecular weight molecules will have only less elution volume, right? Whereas when molecules enter into the gel is interacting, the inner portion of the gel is interacting with the molecule through hydrogen bonding or ionic interaction or hydrophobic interaction based upon the type of the gel what you have used. So you have to use large quantity of mobile phase or large quantity of eluent to disconnect the interactions between the gel and the molecules. You have to use large volume. So larger the volume, you can see say 110 ml of eluent is needed where to elevate say for example say 1 kilodalton, for example 1 kilodalton, right? So for 1 kilodalton you need 110 ml of elution, whereas for approximately 2.25 kilodalton you need only 20 ml of elution, right? So here elution volume is inversely proportional to molecular weight. So you can go for some pure standard molecules with known molecular weight, albumin or lysozyme. So you can prepare molecules with known molecular weight. So you separate using gel filtration. You calculate the molecular weight. It's like spectroscopy. You know, we are using known standards S1 to S5. Similarly, you can prepare low molecular weight to high molecular weight. 5 different known proteins can be taken with their known molecular weight. You separate and you calculate the molecular weight using the elution volume. You plot a graph. So you will be getting a simple regression equation, right? So now you have added the unknown sample and you have purified your molecule of interest and you have spent 60 ml. So 60 ml you apply in the formula, you will get the molecular weight. So this is nothing but, so known molecular weight standards can be used and you can calculate the elution volume for the known molecular weight based molecules, and then for sample you calculate how much ml of elution volume you have used, you apply, so automatically y is equal to the elution volume, you apply in this simple regression equation, you can calculate the log molecular weight. So one of the important application of gel filtration is calculation of relative molecule mass. So I hope the lecture is fine. So any queries you can reach me, you can post. Thank you.